huge thank you, David. That was an incredibly inspirational talk, and I'm hoping that even if we didn't understand every detail, it inspired us in some way to have some hope in terms of what can happen here. I know we're over time. Do we have time for a couple of questions?
Yes.
Yes. Okay.
Sorry, it's just to clarify, it's probably already been answered, but my brain's like, ugh. So you're saying basically it's going back to the O and it not being the ring, sorry. So if it was something in the genetics, that could possibly cause the O, and that could be causing other conditions in other chromosomes as well. But we're just looking, almost like it's a deeper layer of it. Sorry, I don't know if I'm explaining that well.
No.
But then that could lead to the diagnostics of other disease, like you were saying. But is that what you were sort of saying?
Yes, a lot of it. The one thing that I would say is slightly different. We don't think, there is no basis for believing that some other change causes the ring and causes epilepsy. They're two very different things. The chromosome ring happens when cells divide, and you may not know a lot about it, but as you grow, your cells divide, there are more cells, you become bigger, and then that's how the whole business works from the initial conception through to an adult. And that cell division requires that every chromosome gets copied so that each cell has a set of chromosomes going forward. That's replication. Probably the ring is caused by some problem in that process, where chromosomes are supposed to get copied faithfully, they're supposed to divide up and separate into different cells. And something just happens where the chromosomes, because they kind of do this, to divide at every cell division. And if you look, what's happening to the tips? They're not separating. So this is a fundamental cytogenetic phenomenon, and maybe that's the ring 20 fails to do the final bit. So that's a sort of chromosome cell division mechanism. Epilepsy is not that. So I think it's rather, whatever causes the chromosome ring may be just an occasional problem with this process doing the final step with ring 20. And I did mention there are other chromosomes that do this as well, or fail to do this. There are other rings. So I think the mechanism for the ring formation, it's more the other way around. There's a mechanism for ring formation where something is not happening, there's tension in the cell, then there's going to be breakage and damage, and that is what then affects a gene or something and causes the epilepsy.
Yes, I see.
Yeah? So the ring formation is one thing, but the epilepsy is something different.
Yeah, it's happening from something else.
And yet how are we diagnosing epilepsy? By looking at rings.
Yeah.
Biologically, they're unrelated. Now, I may eat my words, but I can see no reason why.
So that process of that happening and that breakage and that damage causing then the genetic mutation, that's happening in other chromosomes, it could be happening in other ones, and that could be the underlying cause of those symptoms as opposed to the actual ring itself.
Yeah. So if your ring breaks a particular gene, my ABCD1 example, there are other mechanisms of mutation that do not involve ring formation that might involve ABCD1, and they will again involve the same epilepsy. And then, as you've alluded to, there are other forms of epilepsy, like Ivan Cameron. Nothing to do with chromosome 20, different gene.
Like the whatever, if it affects a different, I'm going off topic a bit here, but I just mean if it's a different chromosome and it breaks, it could cause a different symptom in it. But it was more the point that it's that process that's happening that is then causing the symptoms, not the actual ring itself.
Yes.
And it could be put onto other different things.
That I think is the most likely hypothesis.
Okay, yeah.
Hypothesis. Yeah. And Alison and I have discussed this sort of issue a lot, haven't we? It's kind of like, what is the ring? And what? So I believe there's a question online.
Brenda has a question.
Does the ring change? I think it's quite possible, because once DNA has been damaged, the cell has pretty good ways of recognizing damage and repairing it. And that process is continuing. It may just be a one-off repair event, or it may be more than one. So there's a possibility that all chromosomes, but certainly the ring 20 can change as you go on. And of course, every cell accumulates new mutations throughout life. That's why people get cancer, because they accumulate mutations, genetic or caused by ultraviolet light or radiation or whatever it is. So the same thing can be happening to any chromosome, including this one. But the initial event for the ring formation may have caused some disruption that then gets repaired in a certain way. The other thing which I think I'm learning a bit more about is that not every cell retains the ring 20. Some cells retain the ring 20, some lose it. And therefore, in a slightly different way, there are changes going on through a person's life when they have the ring. Only a fraction of their cells contain the ring. That's a mosaic, they call it. It's a mosaic where some cells have it and some cells don't. And then there are questions, well, hang on, do they have one ring 20 now, or have they now acquired a second ring, a second 20 to correct the defect? Again, the cell is often trying to correct imbalances. Could it be done earlier? Yes. That opens up a whole new field, which indeed the NHS and the world is talking about with us. And we cut our teeth on children who end up in intensive care, sometimes neonatal, sometimes pediatric. But children coming into intensive care settings, about half of them are the result of a genetic problem. So Jessica was one of those. She wasn't in intensive care, but she was quite ill. And I think the question that we've been asking ourselves is, while we learn all the things that have gone wrong genetically and have the child ending up in ICU, and yes, NHS costing lots of money, what if we could have identified earlier so that we could have started the keto diet earlier or anything else? Then the child might never have gone into ICU, and indeed might actually make a full recovery. Because if you find it early, you can treat it early when it's less severe, and you may be able to prevent ICU and all the complications for that. The reason I jumped on the question is because this area that we're talking about, for the sake of argument, how early can you do the detection? Newborn screening. And that is exactly what we can do. I'm going to waste more time and tell you another anecdote in a minute. But it's up to you. Really? And we are talking about that. It's we already do newborn screening, I think, in the UK for 9 conditions. PKU, phenylketonuria, is one of them, and there are several others, and I can't remember them. In some countries or states, they do up to sort of 60 or 70, so we're somewhat behind there. But we have discovered or worked on the fact that up to 600 conditions could fall into this category of being genetic, so you can find them by genome sequencing at birth. They would cause a serious disease before the age of 5. So we're not going to worry about the ones that will just cause a little bit of discomfort, wrong word, but they're not so serious as to be life-threatening before the age of 5. So we'll only take the diseases which are genetically proven, will cause a serious disease before the age of 5, and for which there are treatments, like keto diets. Those 3 criteria are being used, and when you look at the genome, you find 600 or so conditions that might pass all those criteria. And you can begin to see the ethics that's going on. We don't want to interfere. We don't want to sort of start having selection going on just for other reasons. But if this child is probably going to have their life threatened before the age of 5, perhaps we should do something about it. And the list goes from 9 tested today to up to 600. I suspect we'll end up with about 200 to 300 where we feel confident enough that the information will make a difference, that people will be accepting of this kind of decision to make a difference. But again, it all applies, not just 9, not just 60, but several hundred conditions could be sequenced earlier if parents agree, and we might prevent people getting to ICU. Early detection, more effective treatment, and possibly prevention. So it's a great question, Brenda, I think. Thank you.
20.
Karyotyping was the first test to be involved for almost any genetic conditions. So it has widespread activity. The sort of examples, trisomy 21 is detected, can be detected cytogenetically. We've now moved away from cytogenetics there because we can do it from a blood sample. Non-invasive, we call it, minimally invasive. But absolutely, trisomy 21. 14, 18, 21 are the sort of big 3 trisomies that cause serious chromosome problems, and they're all easily detected cytogenetically. But there again, we've moved away from the cytogenetic test to something else because cytogenetics is quite slow, quite difficult, quite fiddly, quite expensive.
Oh, right.
Yep.
I always had
It is simple in the concept. You just take cells, stick them under a microscope, stain them and have a look.
Okay.
Can't do worse than that, can you? But the only cells that show you cytogenetic defects are the ones that have actually got their chromosomes formed into these shapes, which is only the minority. So you've got to look through a lot of cells on a microscope slide before you find one that starts to show the image. Then you've got to go and find 20 of them. 20 is the typical cutoff point for a cytogeneticist, I think. And then in those 20, you've got to see, right, can I see a ring? And sometimes chromosomes lie on top of each other, so you can't see the ring because it's there all the time. And you look at, 15, 16, it's time for tea. I won't do the last 4. I'll move on. And for that reason, sorry, cytogeneticist, I've been in the cytogenetics lab for several years, so I kind of know it's grueling work. You're doing this day in, day out, looking at these slides. That's why actually automated imaging has helped a lot to take away the pain of staring at these things, and that's getting better. But it is quite expensive. And at the end of the day, as I said at the beginning, the resolution is only 10 million bases, so anything less than 10 million bases. Maybe 5 million if you've got really crack cytogeneticists looking at this. So that's why it has been routine. It's not straightforward. It relies on the human eye and persistence, and it's really hard staring down a microscope for 6 hours a day.
And can I just pick up on that, because you mentioned the first tier point, and that gets to the resolution question, and this was something that David mentioned throughout his talk, was the haystack and the needle in the haystack. And from my perspective, the genome, so David's said this many times, I've heard him talk about letting the genome speak, looking at that whole haystack and letting the genome speak rather than going in looking for something that...
Yeah, the thing about, you said first tier, didn't you? That was the phrase you used. And absolutely, testing has been tiered. Start off with something simple and quick, you may get it, then start with something more complicated, and then spend loads of money to try and get the final one. Now, the first human genome cost $3 billion to do. So we're never going to do that as a first tier test. But if it's the best test, and we can now do it for $1,000 or less, it's suddenly competitive with the cytogenetics. And if you then factor in the idea that when you do the cytogenetics, you're going to miss some of them. Whereas the genome, we hope you won't miss any of them. And one of the key, I want to pick up this word tier because it's a really good phrase. We have talked and campaigned for genome becoming a first tier test or frontline test. We did a fantastic, I didn't do it, my colleague in the US led a study in Mexico where there is no genetic testing at all. And we recruited 60 people in the first study. And we actually found a diagnosis in 2/3 of them, just by doing the genome. Now that's nobody has ever done a 2/3 successful genetic test like that until they're using the genome. And again, now that it's $1,000 and not $3 billion, it becomes possible to consider doing it as a first-line test and then saving both the money and the time on the cytogenetics and the other tests. Because otherwise you'd be weeks away, you'd have spent hundreds of pounds before you say, oh, I still can't see it, I'm going to do a genome. So let's forget all the I still can't see it, let's just put it at the front. And that's why we continue to work on those machines to make them cheaper and, what did I say down there? Fast, accurate and cheap, yes.
That's what we're doing. So we're out of time. I know Samir's waiting online to also talk to us, but thank you so much for your engagement and thank you so much for your questions. I don't know how long you're able to stay, David.
I'll stay.
Okay, so you can come up and at the break, ask him other questions then. But thank you once again.